design, fabrication, and testing of a MEMS Peltier Cooler. So just go over a little outline. What we're going to talk about is, first we're going to talk about the design of it, what is a Peltier Cooler basically, and we're going to talk about the theory, the mathematical theory that goes along with it, my choices in the design of why I pick certain materials and certain design, and the fabrication, and then the test results and analysis of those results. So what is a Peltier Cooler? It's also called a thermoelectric cooler, and it basically runs on the Peltier effect. And what the Peltier effect is when you put a current through two dissimilar types of materials, generally it's an N and P type material, as the electrons move through the N type to the P type in this junction, they gain energy. This energy is in the form of absorbed heat. And then when they go from P type, and what you connect an N type over here, heat is released, and that's a form of dissipated heat. So it's a net flow of heat from the cool side to the hot side, resulting in a temperature difference between those two. Just to note, the effect that is the opposite of that is the Seebeck effect, which is when you have these two materials also connected like this, and there's a temperature difference on each side, you get an output voltage between them. So here's the mathematical theory. This is the main equation that it runs on, and it has three parts. The first one is the Peltier effect right here, and that is mainly driven by the difference in Seebeck coefficients between the two materials you choose, and then the current drive. This part here is the thermal conduction. This is an opposition to the Peltier effect. When you have a difference in temperature between two thermally connected sides, they want to tend to flow and get even. So that's bringing the energy back from the hot side to the cool side. And the other one is just the joule heating of the device. The device simply is basically a big resistor, and when you connect the current through it, it's going to dissipate heat, and the whole thing's going to heat up. So in order for this to work, the Peltier effect has to overcome both of these devices, both of these effects. And as you see, as it gets hotter, you get a larger temperature difference between each side. This effect will increase and essentially limit it to that there is a max that you can achieve. So this is just a little more in depth to the equations. Here's the Peltier effect. The Seebeck coefficient is a combination of those two materials. So you're looking to maximize that, you're looking for a big difference in Seebeck coefficient between the materials. And then the thermal conduction, which is getting geometry here of the thermal device from each side, one to the other. And the thermal coefficient of each of the materials, which is a big part in the design deciding of which materials you want. And then just the joule heating resistors. And another big design parameter will be the sheet resistance, the resistivity, to make sure it's low enough that you can get the current drive to drive the Peltier effect high up, but still limit the other effects and make it work. To test what the temperature is on each side of the device, use resistive temperature sensors, which would be made out of polysilicon. And as the temperature increases, the mobility shown in this equation 1 will actually decrease. And when you combine that with the resistance change, the decrease in mobility will increase resistance. So the hot side will increase, we'll see increased resistance, and the low side will see a decrease in resistance. And that difference in temperature can be compared to the difference in temperature. So this is my mass design. There's 3 layers. The red here is P polysilicon, the black is the contact cut, and the blue is the metal, which I'm going to use as the N-type material, and I chose aluminum. So what's going to happen here is the couple. When a voltage is placed, the current's going to drive down through the metal, go through the contact cut, and back on the polysilicon. And it's going to be repeated 25 times to add to the effect. So it's just going to go zigzag back and forth down this board. And I picked the metal, aluminum, and the P polysilicon mainly because of the ability of our fab to produce those pretty easily, and that they provided enough, a low enough thermal coefficient and a high enough difference in Seebeck coefficients to hopefully produce an effect. So just going over the fabrication, first grew an oxide about 1,000 angstroms to insulate the device from the silicon wafer. After that, deposited about half a micrometer polysilicon, implanted that with boron, and the ideal, I was trying to get 35 ohms per square sheet resistance for the polysilicon. Did a anneal process and grew an oxide, and etched it away. Etched through the oxide for the contact cut, and then deposited the metal and etched that away to flip the device. And also did a sinter process in case there's any native oxide here to make sure that resistance was low and there was no open circuits. So here's the final device. This is just a sun picture of the temperature resistor on the side. And here's a picture through a microscope. The device was about 4 millimeters by 4 millimeters. And here are a bunch of them on silicon wafer. So I took the mathematical theory and I developed a calculator to hopefully get what results I might get. So I was able to put in my material, P-type and aluminum, 25 couples at 5 volts, with the total resistance of the cooler hopefully around 30 kilo ohms. And I got a cold side temperature of about 245 Kelvin, which is about 30 Kelvin max temperature difference. And that's definitely an ideal case. I was expecting some change, but probably not this much. So my actual results, I had a few problems. The big thing that I talked about was the implant, and that I wanted a 35 ohms per square sheet resistance. I did not get that. My devices were around 400 kilo ohms, 300 kilo ohms, which is about 10 times as much as I thought I would get. So looking at that, that might have caused a temperature difference, but it wasn't enough to be measured by the temperature sensors. It would have been very small, half a Kelvin or maybe 1 Kelvin, something like that. I did have one wafer where I measured the resistance, and I thought I got good resistance, got around 10, 30 kilo ohms, and discovered that that was because of an over-etch from my contact cut that etched the oxide into the substrate and shorted out the aluminum polysilicon. So all the probes were all connected through the substrate. So just looking, doing a failure analysis, is that the implant is the biggest part. So in the process, in the mass design, would be to add test structures and add a step to measure the sheet resistance after I've done the implant to make sure it's at that sheet resistance required, since that was so important. And the oxide, the overetch problem, simply just use a larger insulating oxide to easily solve that. So I'm confident that just when these two problems are overcome, that this could still create a working device. Just needs a little more work on it. Just some acknowledgments. I'd like to thank Dr. Fuller, my advisor, for helping me through this process. Dr. Rommel for teaching the class and giving good professional advice and criticisms. And then a lot of people who helped me out in the fab. Patricia Miller helped me out with a bunch of tool certifications to make me more independent in the fab. And Stephanie Bolster helped me out a lot during the factory class, which I did most of my processing in.